Hello, physics students. Welcome again. Um, I want to go over part of the quiz or lesson assessment that you took the other day. Um, One of the questions, right here, the baseball question, still a vast majority of people got the incorrect answer, even though in the PowerPoint that I went over, we talked about this exact question. It's the same question. Remember that momentum is a vector quantity. The direction of this momentum makes a difference. So when the ball changes direction from a positive 60 to a negative 40, that's a change in velocity of 100 meters per second. So it's a much larger change of momentum rather than just that small one. Okay, so let's talk about today's ideas. So today, we're going to talk about the conservation of momentum. Now, we've already talked about conservation before. We had conservation of energy, where energy was changed from one form to another. Conservation momentum is just a little bit different, but it does mean that the initial momentum of a system is going to be equal to the final momentum of the system. Okay? The momentum after an interaction is equal to the momentum before the interaction. So by interaction, we're talking about two objects at least. These two objects are going to interact in some way. They're going to come into contact with each other. And that contact is going to change possibly both of their momentums, but the total momentum of the system after the interaction is going to be the same as the momentum was before the interaction. So here's a formula that goes along with that. Okay, so here we have object 1, right? Object 1 has an initial velocity. Object 2 has an initial velocity. Multiplying those things by their masses will give you an initial momentum. Then there's going to be some interaction between these two objects. After the interaction, M1 is going to have a final velocity, and M2 is going to have a final velocity. So their momentums after the interaction is going to be the same as what the momentum was before the interaction. Okay? Conservation of momentum means exactly the same thing. So let's see how this looks in just a little bit of a context here. Okay? So here we go. We've got a father who is helping his daughter ice skate. He's standing behind her and gives her a strong push. What happens and why? Okay? So you thought my artwork was bad when I was on the smartboard. It's even better trying to draw it here with my screen. Okay, so here's the father, here's the daughter. They're standing together. So now in all of these first instances, our initial momentum of the system is going to be 0. That was a horrible 0. Our initial momentum of the system is going to be 0. Why? Because their velocities are 0. So M1 V1I and M2 V2I, since both i's are 0, that's going to make the initial momentum of the system 0. Okay, so let's talk about what's going to happen. The father is going to put a force on the daughter. Over some little time period, he's going to give her a push. That's going to create an impulse. And that impulse is going to change the daughter's momentum. Now, according to law 3. For every action, there's an equal and opposite reaction. So father's going to push on the daughter. The daughter is going to put an equal and opposite force on the father. The time period that the father's pushing the daughter is going to be the time period the daughter is putting a force back on the daughter. So that force that's acting over the time period, right? That's an impulse. It's going to cause a change in momentum. It's going to cause the daughter's momentum to change, and it's going to cause the father's momentum to change. The change in momentum of both is going to be the same because the force was the same and the time was the same. What's going to be different about those two things? Well, think about it. You ever done something like this? What happens? The daughter, right, is going to go off in this direction with some final velocity. What's going to happen to the father? She now has a positive final momentum. If my total has to be 0, what happens to the father? That's right. He's going to go in the opposite direction. He's going to have a final velocity that is negative. So his final momentum is going to be negative. So when I add these two together, we still get 0. Okay, the initial momentum of the system was 0. After the interaction, after the push, the final momentum's got to be 0. The daughter has positive momentum. The father has negative momentum. All right, so let's think about this. How's their velocity going to compare? Are their velocities going to be the same? Probably not, unless they have equal masses, which a father and a daughter probably aren't. The daughter is probably going to have a smaller mass than the father. So the daughter is going to have a larger velocity in magnitude than the father. But their momentum, the impulse that they each got, their change in momentum, is going to be the same. I use those terms interchangeably. Change in momentum and impulse. Remember, they're equal to each other, right? The change in momentum and the impulse are the same thing. They're equal to each other. So let's see what that means in terms of numbers now. Okay, let's take a look at some numbers. So let's suppose the father has a mass of 85 kilograms and the daughter has a mass of 33 kilograms. And after the interaction, the daughter was going at 2.1 meters per second. Okay, so again, M1 V1I plus M2 V2I. Sorry, my writing's not very good right here. M, whoops. M1 V1F plus M2 V2F. So the father's mass, 85, times his initial velocity, 0, plus the daughter's mass, 33, times her velocity, 0. Both of those are 0. Gives me a total initial momentum of the system of 0. So over on this side, $85 V1F plus 33 times 2.1. That's still going to be 85 V1F plus 33 times 2.1. $69.3 spheres of momentum. Okay, so subtracting this over to this side, we're going to get a negative 85 V1F equals 69.3. Dividing both sides by that negative 85 is going to give me, yep, all right, let's get rid of my little squiggly line here. Okay, so again, dividing both sides by the 85, or the negative 85, is going to give me a velocity of the father of negative 0.815 meters per second. Okay, so again, this all ties back together with what we've been talking about in last chapter and the chapter before, where the force acting on an object, what's the force do? Create an acceleration, a change in velocity. The force that the father puts on the daughter is the same as the force of the daughter on the father, right? Equal force on a larger mass creates a smaller acceleration, a smaller change in velocity, and the daughter has a larger change in velocity. So the daughter goes flying off at 2.1 meters per second, while the father moves backwards at that 0.815 meters per second, so negative. Okay? There's not going to be any problems for today. For tomorrow, there's going to be another little lesson assessment. And then on Friday, you're going to have a worksheet where there's going to be some questions that deal with impulse and the change in momentum and this idea of conservation of momentum. But for all of these problems, the initial momentum of the system will be zero, like it was in this problem, right? Both objects are going to start at rest. Something's going to happen, an interaction between the two. One's going to go in the positive direction. One's going to go in the negative direction. Positive momentum plus a negative momentum. The total is going to stay zero. Okay? And next week, we'll talk about collisions, and then we'll really start to have some fun. Okay? Keep up your good work. Keep handing in your assignments. I'm pretty much making sure things are getting graded every day, so your grades in eSchool are up to date. Remember, you can always go back and complete any of those things you haven't completed for this marking period. Mid-marks are coming up at the end of next week,